Hello there, and my name is Jialin Wang, and today I'll talk about my research about ornithological identification with convolutional neural networks. So, as we all know, biodiversity is rapidly decreasing because of human factors such as climate change and habitat destruction, and many species are becoming endangered or extinct, especially birds. And scientists are working their best on the conservation of these species, but they face many problems, and one of which is how they monitor the wild species populations. And sometimes it is difficult to constantly monitor species due to various factors like the geographic location. And I think one of the possible solution is using camera and image classification techniques, which will be the main focus of this research. And this research will aim to identify 10 different species of birds based on their images using a machine learning technique called convolutional neural network. So here are the 10 species of birds that are identified in this research, which are the American crow, the blue jay, the Vermilion flycatcher, the western grebe, the yellow warbler, the cactus wren, the eastern tawkee, the indigo bunting, and the California eagle, and the ruby-throated hummingbird. And now let's move on to the methodology of this research. So the data source is from a database called Caltech UCSD Birds 200, which includes about like 60 images for 200 species of birds. And for the sake of simplicity, this research is only concerned about the 10 species that are previously mentioned. And before we move on, let's have a crash course on what exactly is a convolutional network. So basically, all you need to know is that it's a machine learning technique that has a similar structure to a human neural network. So what you see on the top right corner is basically a structure of a simple convolutional neural network, and on the leftmost side, which is the input layer, and you fill this inputs with a bunch of numbers, and these numbers are basically converted from the image data sets into number arrays and passed on through the layers. So each different layer has like a different activation function, which does something on the number based on what the activation function is. And these activation functions are decided by the programmers in order to achieve optimal performance. And it can usually alter the dataset in some way to increase the accuracy. So you see that the images are basically like 2D arrays of pixel values, and there are different types of layers. Some process the images in 2D form, and some like flatten it out into a long 1D array, and some just simplify the dataset, and et cetera, et cetera. And eventually they pass on through the layers and get processed through every time they enter a new layer, and they end up on the rightmost layer, which is the output layer. So in this picture, there's only one node in output layer, but in this research, there's actually 10, which is represents the probability of the images being each type of bird, and the program will make a final judgment on the classification based on the likelihood, like how likely is it to be like a crow, and how likely it is to be a hummingbird. And basically, long story short, is that this neural network goes through a complex series of calculations to make sure that there is minimal error. And another thing is because the data is sort of limited, so the data set also goes through a step of data augmentation, which is a step of artificially creating new data based on given data. And this might sound a bit complicated, but oftentimes it's just basically like flipping its images sideways or mirroring. And it might basically make no difference to the human eye, but to the computer, it's very useful because it basically doubles the set of training data, which can often significantly increase the accuracy. For example, here are the ROC curves before and after the data augmentation. On the left is before, on the right is after. And so the ROC curve is basically a way to evaluate the performance of a model. And so the vertical axis here is a true positive rate. And long story short, it's a value we want it to be as high as possible. And on the horizontal axis is the false positive rate, and we want it to be as low as possible. So you can probably see that the better the model performs, the closer the ROC curve is to the top left corner, and you can see like there's a huge improvement. Like all of these curves have gotten like significantly closer to the top left corner after the augmentation. And the train test split is set to a ratio of 80-20, which means that the whole data set is split into two sets. And the training set is used to train the machine learning program, while the test set is used to test the validity of the results. So basically, we want to make sure that the model is applicable to as many examples as possible while maintaining the highest accuracy. And there are some previous research done on the topic of bird identification with machine learning. For example, this one is there's a previous research done by A.M. Horst, A.P. Hill, and K.B. Gorman. They aim to classify like 3 different penguin species based on a different data set. However, there are some main differences between this research and that research. For example, this research contains 3 species of penguins, and the data is numerical instead of images. And it also used k-means clustering to classify, which is another classification algorithm than convolutional neural network. And for my research, it's the data set contains 10 different species, and it's based on images. And now let's move on to the results of my study. So the final version of the model has a fairly high accuracy of 70%, which means that it makes correct predictions on 70% of the images. And another way to represent the results is a confusion matrix. So you can see here the vertical axis is the true label, and the horizontal axis is the predicted label. So the true label is what the image actually is, and the predicted label is what prediction the computer makes. So each bird is assigned a number from 0 to 9. And so, for example, on the bottom left corner, the true label is 9, and the predicted label is 0. So it means like there are 2 images that are supposed to be ruby-throated hummingbirds, but the computer mistakenly classifies as American crow. So you can see like so you can probably see we want as many things across the diagonal from the top left to bottom right, because the two labels match, which is a correct prediction. And you can see overall most of the data lies on this diagonal, which is a good sign. And here's the final version, ROC curve. So you can see like most of the curves are close to the top left corner, as previously mentioned. And another method to determine the performance of the model is the AUC, or the area under a curve. So it's basically a number from 0 to 1, and we want it to be as high as possible. You can see the numbers are pretty good, like for each bird species. For example, 0.93 and 0.88. And the micro average AUC, which is like basically the overall performance of the model, is 0.83, which is also pretty close to 1. So that's pretty good. And this study has a great potential for a wider implication, because if this model can be trained to identify 10 species of birds, it can be trained to identify all 200 species of birds in the dataset if given enough computational power. And convolutional neural networks can also play a crucial role in environmental preservation, because they can be trained to identify endangered birds, making it easier and more efficient for scientists to report rare bird sightings via camera. And that's pretty much it. And thank you all for your attention.